Hello, everyone. My name is Ryan Keiper. Welcome to my talk, Chasing AlphaZero, Beating Myself in Chess Using Neural Networks and AWS SageMaker. What I want to talk about today is the challenge that I gave to myself at the beginning of this, a little bit about some chess history, what even is AlphaZero, the different machine learning flavors, the different types, the type that I'm going to talk about today versus the other two that might be more familiar. The type that I'm going to talk about today is called reinforcement learning. And then my process building a chess bot, the challenge that I set for myself first of all. Here I am, that's me. I'm a chess guy playing a tournament there. And I'm super interested not just in the world of chess, but also in chess engines that people create to play against other humans, engines pitted against engines to create the strongest engines in the world. It's a fascinating world to chess nerds like myself. So I was interested to see if I can create something like this, but more interestingly, I was interested to see the general space of machine learning, something I'm also interested in. I didn't have a lot of background in this, and I wanted to see how quickly can I get up to speed in this world and apply it to a problem that I like, chess and chess engines. So that's the real challenge here. Are the resources available for me to get up to speed on this quickly? First, though, some nerdy chess history. We may all remember Garry Kasparov and his epic battle with the machine, IBM's Deep Blue, and how the machine finally toppled the king of the chess world. But since then, engines have become ubiquitous. I have an engine on my phone that is orders of magnitude stronger than the IBM engine that they brought against Kasparov. So why are we even discussing this? Chess engines are long since superhuman. Well, at the end of 2017, hilarious as it is to say, Google rocked the chess world with the release of its AlphaZero, a program that was not built in the typical engine way. Normally, when you're building a chess engine, you give it a book of the common openings, a table of how to play the endgame, some strategies for what to do in the midgame. This wasn't built that way at all. This engine was given the rules only as constraints and allowed to experiment in that world and play against itself millions and millions of times and learn slowly. And then it was pitted against the world's strongest engine ever created, Stockfish, and it blew Stockfish away. In a 100-game match, AlphaZero didn't lose a single game, which was just stunning. So that's what really drew me to this is my goodness, reinforcement learning can do that. I want to see if I can do that. So now here we are. First, though, I've said the word reinforcement in terms of this flavor of machine learning. Let's talk about the other ones first, just so that we know what we're talking about. The three flavors of machine learning are generally thought of as supervised, unsupervised, and then this new one, reinforcement. Supervised machine learning tends to be, if I've got my network here, I eventually want it to be able to make predictions. So I give it a lot of labeled data. If I have a bunch of pictures of cats and a bunch of pictures of dogs, I give it a picture of a cat, and it says, was that a dog that you gave me? But because I have the label on it, I can say, no, you got it wrong, please correct. And it goes and it corrects the math slightly that led it to that answer. And if it does that a million times, then it can reliably, on new pictures, say, that's definitely a cat, that's definitely a dog, and be correct and make these predictions. Unsupervised machine learning, however, you don't work with labeled data. So you give data to the network, and when it gets to the end, it's not able to correct because it doesn't have the right answer, but it is able to group that data and say, I think these are all pretty similar, I think these are all pretty similar, and then these are outliers. So it's good at finding anomalies in data sets when you use this unsupervised version. Reinforcement learning is a bit different because it's not just the network, it's a system that we're using here. We have an agent and we have an environment, and the agent gets to play around in the environment, trying different things, seeing what actions cause what reactions, and then that becomes the data, the pairs of it was in this state and I did this action. That's the data that gets fed into the network, and then the network uses that data to tell the agent, hey, next time you're in this position, try moving your pawn this way instead. So that's how reinforcement works. It sort of borrows some ideas from supervised, but it's a broader system. If you're interested in this topic, by the way, Ryan Gross, one of our other speakers, is also doing a talk on this. So if you get the chance to catch his as well, he's got a lot of great ideas in there too. So check that out definitely if you get a chance. Some real-world applications of reinforcement machine learning. Recently, this was used to treat sepsis in hospitals, which is notoriously difficult to treat and very patient-specific. These types of systems are the mind behind how self-driving cars learn to stay within the rules. Any task that you can approximate with a simulation of some kind tends to be a really good problem that this type of solution would solve well. I've said network a few times now, but we may not know what that is yet. Let's take a look at what a neural network actually is. I don't want to dive too hard into the math or how it actually learns or works back and forth, but I will give you some excellent references to look back on and dive in harder on that for yourself. But basically, we'll think of this as a tool that we can use for our purposes. As long as you can give it the correct hidden layers throughout, and you can structure your data as a series of digits that you can feed into this input layer, then you can use this tool in this way to do either supervised or unsupervised learning, or to combine it as part of a system and try some reinforcement learning. Let's look at reinforcement learning more closely. I've talked about some of the broader pieces to it, but let's see if we can see what some of the ingredients actually are. Here we have a classical representation of our agent, Mario, the perfect example. Mario would be running around his environment, trying actions at random at first, and for each state that the game is in, Mario tries an action, he gets a reward or punishment, and the game moves to a new state because of his actions. Those 4 pieces of data, the state it was in, the action he took, the reward, and the new state, those all go into Mario's memory. Mario has a memory, and each of those chunks goes into it. And once that memory fills up a bit, Mario also has a network. And that network begins taking random samples from that data and using it to learn in this supervised way. I was in this state and I tried this action. What reward do you think I'd get? I think this reward. Nope, you got it wrong. I've been in that state before. I can see you get a different reward. So it's able to correct and teach Mario, oh, he needs to go in a different way next time. So, and then as time goes on, he makes fewer and fewer random actions because he's taking more actions from the network. I want to pause for a minute and say why it's important that he needs to continue to sometimes take random actions and sometimes take network-guided actions. Let's talk about chess again for a minute. Let's say I'm in a position where I've gotten to this position many times, and every single time there's a pawn right there that I could just take, and that'd be awesome. I get a point, I get a reward as a system. I love that. But if I just don't take the pawn and I just go over here, I could get checkmate, and that's way better. But the system will never see it if it keeps just going for that immediate reward. You need some balance there so that sometimes it chooses random actions to explore a bit, and sometimes it chooses those policy-driven actions. So the network, this is one of the other pieces. And sometimes agents designed for more complicated problems actually have more than one network, more than one brain, where they use them in tandem to combine to solve very difficult problems in more efficient ways. So the levels of complexity here are building, but so is the efficiency. And then we have what I mentioned as the environment. This is where Mario lives and explores. And if you're setting up a system to solve a problem, designing the environment can be one of the most difficult pieces to this. But once you have the environment set up, you can definitely run a simulation like this, and this can be a great solution to the problem. OpenAI Gym is something that I'd like to highlight as a really great tool right now. It's an open source place where people have written a bunch of different environments that you can use and where you can write your own environment. This is something that I'll lead into now, basically. which is how do all of these abstract ideas translate into code? Well, first of all of these different pieces that I've talked about so far, these are just Python classes. It's all Python code, and there are other languages that people can use, but it seems like Python is the most prevalent. And however, Python is not necessarily it's not the only tool to use, and some people can get very intimidated by the number of tools that are required to get started with machine learning and build something solid. So just seeing that number of tools can be like, I'm not sure where to start or how to get all these working together. So let me talk you through my process a little bit and see if I can shed some light on that a little bit. Firstly, where did I even write my code? Well, if you're not familiar with Jupyter Notebooks yet, Jupyter Notebooks are awesome. They're sort of the go-to for writing Python and doing it for an ML purpose and doing some data visualization where you can showcase the results of what your code has done. It's a great scratch pad. It's also a great presentation tool. And it's becoming a go-to for when people work in this space. But I didn't just use Jupyter Notebooks. There's some limitations if you're trying to get a Jupyter Notebook set up locally. You can run into some Python dependency issues. I love Collab. If you've used Jupyter Notebooks but you're not super satisfied, I love Collab because it's up in the cloud. It makes all of your dependency issues atomic per project, which is wonderful. You can share this on Google Drive, share your notebook with other people, and have collaboration that way. So most of the code that I wrote was in Collab, which was an awesome experience. So let's talk a little bit about some agent code. I don't want to dive, again, too hard into line by line of code, but I thought this particular piece was pretty elegant. This is the random actions versus picking from the network. So when Mario's like, am I going to make a random action or am I going to choose from the network? We have this value called epsilon. And the first time it runs through a series, epsilon starts out really high, and then slowly epsilon gets smaller and smaller. We just subtract a little bit from it every time. And every time we run through a simulation, Mario or the chess player selects a random number, and then from that, if that random number is lower than epsilon, take a random action. If it's higher than epsilon, choose from the network. So I thought this was a really elegant way for you to continue to take random actions over time, but just less frequently, less statistically likely. There are also a number of ways to code your network. So in thinking about writing your network, there are several different frameworks that we can choose from. Keras, TensorFlow, PyTorch. These are all super popular frameworks for writing your network right now. I chose Keras, and I thought it was awesome. This network here, for example, how many lines of code would you suspect that it would take to create a network like this? Well, with Keras, it was a handful. It's super easy to create a network. I import a couple objects, then create my model. The word model here I use to be interchangeable with network. Model is sort of your code representation of your network. I add a few layers to it, and then I compile it. And then that's it. That's all you have to do, and you've got your network, and it's ready to train. And then all you have to do is have an environment to pit it against. You've got your agent, and you've got your network, so your agent has a brain, and now it just needs an environment in which to play. So let's turn to OpenAI Gym. OpenAI Gym is a great tool. You can see a bunch of different environments here that it's got available, everything from sort of ASCII representations to old Atari games. It has Doom, scenarios where you've got sort of a 3D creature and you're trying to teach it to run across a space without falling over. A bunch of different simulated environments that are great for learning and great for taking the agent that you've built and pitting them against a challenge. As well, OpenAI Gym has an easy-to-follow API that if you'd like to create your own environment, all you have to do is follow this API. It needs to have these 4 methods. The environment can initialize itself with a few parameters. It can take a step, which means the agent says, here's the action I want to take, and your environment says, great, here's the state that produced. Your environment can also reset itself back to the beginning, and it can render itself so that us humans can actually see what's happening. So up to this point, when I was working on the different code pieces, this journey was kind of a struggle up to this point. I was following sort of a blog post over here to try and get my agent built, and following a YouTube video over there to try and get my network built, pulling in this chess environment that was up on GitHub that was OpenAI Gym based, and the three were just not playing nicely together, and I was kind of stuck. But then I found a framework called Coach, which saved my life here. Coach is amazing. This is a product put out by Intel AI Labs, I believe, and is a massive framework for basically plug and play all of these pieces that you want to put together in a big system. You have them. For example, here are the sheer number of agents that they make available to you. And when I say agent, what I mean is these are different. These are agent. It's like, oh, you want an agent with 3 networks that all play together in this way. Oh, you want this one that's designed to solve this particular purpose. Cool. You can just take them and plug and play. I used one that was the actor-critic model, which one network is taking in state, trying to decide what the best action is. The other network is sort of judging those and saying, assigning quality values to the different actions, and then the two networks compare notes every so often. So that's unbelievable, and probably would have been beyond my ability to code on my own, but I don't have to. It's available right here. So I'd like to talk about SageMaker a bit, because when I started this process and challenged myself to this, I thought SageMaker, that's definitely the go-to spot for all of these pre-built options for getting ML solutions up and running. Surely that's where I would go for this. And if I was doing a supervised or unsupervised project, I definitely would have turned there. You can get a Jupyter Notebook instance up and running. You can run your training jobs. You can pull in any number of pre-built algorithms for facial recognition, for Bitcoin trading. They're optimized for a ton of different things. And then you can bring in models from outside of SageMaker, and you can expose them on an endpoint, as well as during the training, expose them to a massive amount of hardware acceleration so that they really get the power they need to train up really fast. I thought this was going to be a perfect solution, but I just didn't end up needing it. I worked in Collab, and I pulled in Coach, and I was able to get my solution up and running. And here's what that solution looks like. If you were expecting a wildly impressive UI, not only is that not what this is, but that's not what we want. You don't want it to waste computing power on UI. You want it to just spin as many times as it possibly can. I have it rendered here so that we can see a little bit of what's happening. These 4 grids are 4 chess positions. The lowercase letters represent the black pieces. The uppercase represents the white pieces. In the top frame, you see black has a king, a knight, and a bishop remaining, and white has a king. Then white takes black's knight. Black only having a king and a bishop remaining is not enough material to get checkmate, and so that ends the round. You see a few statistics here about the reward that it achieved, the number of steps it took to get there, and then it resets the board and it goes on to the next one. So who won? Well, I'm sorry to disappoint, but I ended up being the victor. My bot did not reach human play strength, but I don't think that it can't. I think there's an enormous amount of potential here. Once I figure out a few more bugs on my end and I put some more computing power behind it, I think it could get there. I think it was close. I think Coach is an amazing framework to work with, and I think it can definitely get there. So I promised you a few more resources for how to dive in deeper after this talk. And here they are, basically. These 3 video sets were all I needed to get a massive primer on understanding all of these pieces. The content by 3Blue 1 Brown, Neural Networks, and then anything by Deep Lizard, but all of their video series on machine learning and reinforcement learning were amazing. So I highly, highly recommend those. And then I also recommend you just experiment with the tools yourself. Get your Python skills out. Get Jupyter Notebooks up and try playing around in Collab. Play around with what's called the MNIST data set, which is sort of the hello world for getting a supervised learning setup going. And then see if you can play around in the reinforcement learning space. Get an agent and get a model, pit it against some OpenAI gym environments, and play around with it. This journey for me was absolutely amazing. 3 months ago, I had no idea about what I was doing in this space, and I was able to come up to speed on it and build a system like this. So I think you can too. If you're interested, definitely dive in here. Highly recommend. Thank you very much for your time.